Hey everyone, I want to take a quick minute just to tell you about something that's going on this weekend. Recently, Ranty Flat Earth decided that he's going to open up his platform to globe earthers to present information that they feel validates their beliefs, and then initiate a discussion afterwards so that we can actually have a conversation. This is a very noble gesture for Ranty, and I applaud him for it, but I'll let him describe what the intent of this endeavor is.
Okay, so going forward, a lot of my subscribers were going to be asking what my next line of research was going to be. And because I've spent so long doing optics, I really didn't want to spend too much time finding out all the ins and outs about other people's beliefs and why they believe in certain things and what their proofs are. So, being a part of the Flat Earth debate team has been great. More recently, though, we haven't had a thorough discussion with the Globers. So I thought, well, how about I open up the platform in a way that allows them to come in, and I mean this from the side of the Globers, and to concavers and to flat earthers. So it's literally open to anybody to come onto my platform, do a live or pre-recorded actually presentation, anywhere from 10 minutes to 45 minutes in length on a very niche specific topic involved with flat earth. So it could be like gyroscopes, or it could be about gravity, or whichever it would be, and give their reasons in detail with a presentation exactly why they believe in that for their model. So a Glober can come on with their reasons why they believe gravity is real in regards the model for the globe. And then the format's going to be that they come on, they do a presentation. I don't interrupt them a single bit. In fact, I won't ask them any questions in the entire thing. So they come on, they do the presentation. We then open up the conversation to the chat people and we ask them, can you ask some questions? So people will ask some questions. The guest will then decide whether or not they wish to answer it. If they don't feel they can answer that particular question, they can choose to ignore the question or just say, I don't know, I'll find out, or whatever. And then we'll end that particular segment. So that will be finished then. So that will be one show done and dusted, where a Glober has come onto a Flat Earthers channel, told my audience and whoever decides to show up at the time why they believe in a certain thing.
So I immediately sent Ranty an email saying that I'm game. I sent him a list of the general topics that I'd covered in the past and let him choose which topic he would like for me to present. Ranty selected the Southern Hemisphere. So what I'm going to present to you now is what I will be presenting to his audience on Friday night. Time of the event is 9 p.m. London time. So if you'd like to tune in and see how his audience reacts, I invite you. I'll be there watching as well and answering questions that anybody could have. So the following is a combination of 3 videos I've done in the past, all that support that the Southern Hemisphere demonstrably proves the Earth is not flat. Today we're going to take a look at time, the sun, and navigation. First, let's look at the history of time. In today's modern age, everyone has become accustomed to the base 10 metric system. But have you ever wondered why there are 24 hours in a day, and 60 minutes in an hour, and 60 seconds in a minute? Egypt is generally credited with being the first culture to divide the day into smaller parts around 1500 BCE. However, when they did this, they used a base 12 system. The exact reason for the ancient Egyptians' value of the base 12 system isn't known, but there are several theories. Some believe it was based on the 12 lunar cycles in a year, while others actually believe that it's based on the 12 joints in your fingers on one hand, when you exclude the thumb. And with the joint method, you can actually count to 24 by using both hands. Early Egyptian sundials divided the day into 12 equal parts of sunlight, but these parts would vary in length based upon the time of year and the amount of sun you were receiving. Nighttime was similarly divided into 12 hours through various celestial objects, And once the concept of a 24-hour day was in place with the Egyptians, it just kind of stuck. The idea of fixed hour lengths didn't begin until the idea of heliocentrism began with the Greeks. Astronomers needed fixed time to document their observations at night. Around 140 BCE, Hipparchus proposed to fix the length of an hour into 24 equal parts, day and night, as measured on the equinox. While astronomers began to use this method during the time of the Greeks, laypersons continued to adjust their hours to the daylight hours until the 14th century and the advent of the modern clock. When dividing the hours into subparts, Hipparchus and the Greeks used a Babylonian system of base 60, which they had inherited from the Sumerians around 2000 BCE. This base 60 system was also used for measuring angles and continued in mapmaking and geographical coordinates. Around 200 BCE, Eratosthenes used this system to divide the globe into 360 degrees, allowing for proper identification of one's location on a map. These degrees are today's lines of longitude, and measuring them is the point of today's video. How are these lines of longitude used to find your location on land? Easy. The sun and time. At any given time on the globe, or even on an AE map, the sun is directly over some point on the ground. This is called local noon. And by knowing the track of the sun for your location, and being able to identify exactly when local noon is, you can identify your longitude. But how? Remember, the day was divided up into 24 equal parts. The sun travels 360 degrees around the globe, or across the plane, in that 24 hours. So this means that the sun will travel 15 degrees per hour relative to the crown. And this works on a globe and on the AE map. But to identify your point on the map, you need a fixed reference and an accurate knowledge of time. Today we utilize Greenwich, England as our fixed point. So that is what we will be using for this demonstration. And we'll even use it on the Flat Earth map. To begin, we will start with noon at Greenwich, which is 0 degrees longitude. For every person standing on 0 degrees longitude, this is the time of day when the sun reaches its highest climb into the sky. Again, local noon. Using a very accurate clock, if we allow 1 hour to pass, the sun will travel across the sky and will now be at 15 degrees west. At 15 degrees west, it is now local noon, and at Greenwich, it is 1 p.m. If we let 5 hours pass, the sun will be directly above 75 degrees west. This line of latitude is now at local noon, and Greenwich would be at 5 p.m. Knowing this information, we can identify where we are at on the globe or a plane. Here are the 2 keys to being able to identify the longitude for yourself. 1, you need to be able to identify what time it is for you. This could be done through various methods such as observing the sun's track through the sky. Galileo even proposed using the orbits of Jupiter's moons as a universal clock. And number 2, you need to know exactly what time it is in Greenwich, England. If you were to measure your local time and determine it to be noon, and then look at your Greenwich clock and determine that at Greenwich it's 9 a.m., you would know that you are 45 degrees east of Greenwich because of the sun travel time. The exact location even continues with the clock analogy with minutes and seconds. The Statue of Liberty is located at 72 degrees, 2 hours, 44.33 seconds west of Greenwich, England. This principle is the same on a globe or on an AE map. But here's where we run into some problems, and they're pretty big ones. On a globe, these lines run between the North and South Pole. Near the pole, these lines get closer and closer until they actually intersect at the pole. At the equator, they are the farthest apart, before narrowing down again and converging at the opposite pole. But on the AE map, the most widely accepted view of the flat Earth, these lines of longitude don't reconverge at the South Pole. They just continue to go on forever as they pass the equator and get wider and wider. And here's what the math says about the AE map. Viewing the AE map in 15-degree segments, because this is the 1-hour travel time of the sun, the distances between 0 longitude and 15 west are, at 70 degrees north, 577 kilometers. 50 degrees north, 1,155 kilometers. 30 degrees north, 1,733 kilometers. And at the equator, 0, 2,599 kilometers. These measurements were based off of a 15-degree triangle and are indisputable. Measuring the distances from the North Pole to each of these lines of latitude are what gave me these distances between 0 and 15, the open end of the triangle. Now, these measurements alone cause a problem, because using spherical geometry, the same distance at the equator is actually 1,642 kilometers. We've gained almost 1,000 kilometers of land between 0 and 15 at the equator, distance that by all accounts for humans that actually live on the equator doesn't exist. Our problem gets even worse as we go past the equator. The AE map forces this 15 degrees to continue to grow almost exponentially. This is what these distances look like. At 30 degrees, we have a 2,000 kilometer gain. At 50 degrees, we have a 3,000 kilometer gain. And at 70 degrees, we have over 4,000 kilometer gain. Much of this land is out to sea or in the fictitious land of Antarctica. How does this actually look in reality? Let's take a look at Australia, the upside-down country that others will still claim doesn't exist. And for this project, we're going to take a look at Sydney and Adelaide. On a globe, the direct line distance between Sydney and Adelaide is about 1,157 kilometers. This is at the 34-degree longitude line. This places the straight line distance between Sydney and Adelaide on the AE map at over 3,000 kilometers, a gain of more than 1,900 kilometers, a gain that no person has ever documented on the ground. And this isn't a no man's land. It's not like it's out to sea that has no roads. There are modern paved highways between Sydney and Adelaide. And to date, no Australians have complained that they ran out of gas driving between these two locations because the road was actually longer than the maps claimed them to be. But what about flights? Let's take a look to see if there's any flights between Sydney and Adelaide. And wouldn't you know it, there are. At least once every day or two. And these are real flights with real people that get on a plane at one city and get off a plane at the other city. And the travel time between these two cities is about an hour and a half. For this flight to fit into the flat Earth world, that plane would need to be traveling at an average speed of 1,924 kilometers per hour. That's not max speed. That's average speed, takeoff to touchdown. Max speed would be about 200 kilometers an hour faster. Now, flat Earth gods like Jaren will claim that we don't really know how fast planes can fly, but until he can show me a commercial jet that has a max speed of over 2,000 kilometers an hour, a speed approaching Mach 2, he doesn't have a leg to stand on. Our old friend Jaren has found an article that he believes proves his feelings of the Southern Hemisphere and how planes can actually get from Australia to South America. So let's see what Jaren has to say.
What's going on, everyone? It's Jaren from Jarenism, back with a short video for you. A video where I will be showing you a recent article that allows me to feel, in a way, kind of vindicated. A while ago, when talking about planes traveling in the Southern Hemisphere, I stated that those passenger planes could be traveling faster than the speed of sound and actually be traveling much greater distances without anyone knowing. The jet stream is moving so fast right now that commercial planes are traveling faster than the speed of sound. If you're flying east today, you're in a whole lot of luck. The jet stream, that funny little channel of high-altitude air that flows over the United States and northern Atlantic, is moving at unheard-of speeds, delivering commercial jets to their destinations nearly an hour ahead of schedule, the Washington Post reports. In fact, one Virgin Atlantic flight traveling from Los Angeles to London notched a speed of 801 miles per hour over Pennsylvania, which, had it been on the ground, would have been faster than the speed of sound.
Well, maybe he's got something here, because if planes can actually travel that fast, maybe they could traverse the distances of the Southern Hemisphere required on a flat Earth.
All right, here you see I've brought up Flight Radar 24, which is a site where you can track flights, and I've just typed in Sydney to Santiago. And if we zoom in here, you can see what happens. And the problem that we have with these flights is that as soon as they take off from Sydney, it gets out over the open water and, of course, drops off and just skips to that next location. And then it will fly over New Zealand there. And again, once it gets to a certain spot, it just disappears from radar until it appears all the way on the other side over here by Santiago, Chile. So again, you can see that this plane got up to almost 680, I think I saw 684 miles per hour ground speed, and then it disappears. So we have no idea how fast this plane could be possibly traveling once it gets up high enough to be in those jet streams and traveling across the Southern Ocean. And then you don't see it till it hits the other side. So we have no idea what's happening in this downtime where the satellites can't pick up, I guess, the speeds of this plane. And so this is just a little quick example that I made here. Let's say we've got a plane going Sydney to Santiago, as we just showed. That travels 7,000 miles in 12 hours, which is about the average flight time. 7,000 divided by 12 equals 583 miles per hour. All right, but what about the jet stream? So remember, it's helping the plane with close to 250 mile per hour winds. So if the plane is being helped, well, 583 miles per hour minus 250, is the plane actually going 333 miles per hour? And then it's getting the extra 250 to end up at 583? Well, that doesn't sound very efficient, does it? So let's look at it this way. What if that plane was actually going 625 miles per hour, which we saw, ground speed. We also know that that's easily under the speed of sound. 625 miles per hour plus 250 miles per hour, which would be the most efficient thing, is 875 miles per hour ground speed. Okay, so a plane from Sydney to Santiago could be going 875 miles per hour for 12 hours. 875 times 12 is 10,500 miles instead of 7,000 miles. I mean, quite a difference, right?
So Jaron is questioning the distance and speed of the airplanes as located off of New Zealand and off of the coast of Chile. So let's take that information and see what does it tell us with basic geometry. So here's our location off of New Zealand, a little bit off of the coast, kind of like Jaron showed. This is about the point where it dropped off of the GPS. And then we've also got our location off of Chile. Now, to figure out this in geometry, we need the distance between the North Pole and that spot off the coast of New Zealand. And when we measure that, we find that it is 14,846 kilometers from the North Pole. So that is our measurement number 1. Now we have our location off of Chile, and you'll notice that it is a significant distance farther north on the map. We'll just say that rather than a globe. And the distance between that location and the North Pole is 8,798 kilometers. So we now have our distance 2 for our triangle. Now, on a globe, the distance between these 2 points is 8,800 kilometers. Now, I know Jaron used miles, but I'm trying to stay international here, so we're going to have to do a little conversion. This unaccounted for time, when the satellites don't see this plane, is just over 8,000 kilometers. So the next question we have to ask is, how far apart are these locations? Because on the globe, like I said, that's just over 8,000 kilometers. But if you use flat Earth math, first we need to know how far apart they are in degrees. And based upon basic map making, these 2 locations are 102 degrees apart. Now when we create our triangle with sides of 14,846 by 8,798 with an inner angle of 102.7 degrees, the distance between these 2 points is not 8,080 kilometers. It's 18,396 kilometers. So how fast would a plane have to be traveling to traverse that distance in that time? Well, I'll be honest right now and let you know that when I did this math initially, I didn't think it was that big of a difference. Because when you traverse that distance in 12 hours, you only get a speed several hundred kilometers an hour faster than Jaren is claiming, which is still more than any jet plane has ever claimed to travel. But what I'd forgotten is that it's a 12-hour flight from airport to airport. But we're not measuring airport to airport. We're measuring unaccounted for space over the ocean. And that time was only 8.5 hours. So in that 8.5 hours, this plane had to traverse 18,396 kilometers. And when I use Jaren's math, 18,396 divided by 8.5, how fast does our plane have to be traveling? It's not the 1,289 kilometers an hour converted that Jaren claims. It's 2,164 kilometers per hour. Unless you can find a jet stream that has a speed of 700 kilometers more than you're thinking it does, your math doesn't add up.
And now you see why anyone who says Southern flights prove the globe are either too scared to consider the alternative or just haven't researched enough.
MarineTraffic.com is an amazing website similar to the air traffic websites. It shows you virtually every boat that is on the ocean. And just like a lot of those other websites, it is a pay website with specific free features. By paying for the service, you're allowed to look at virtually any boat and their current and exact location on the ocean. Well, I'm a poor soldier, so I'm not going to subscribe to a website just so I can track boats. But as part of their free service, you are allowed to select boats that you would like to follow. And with that, they will send you an email once a day with the location of that boat, up to 30 updates per month. Now, those updates also include entries into harbor, exits of harbor, docking, mooring, so you may get 5 to 10 notifications in one day as your boat enters a harbor. So as part of this project, several months ago, I wanted to find a boat that was traversing across the Southern Hemisphere. And I found this boat, the Olivia Maersk. It was in New Zealand, and it was getting ready to sail across the Pacific to the northwestern coast of South America. I subscribed to the website, I signed up for this boat as a tracking, and then I just kind of forgot about it. And I got emails every day. I just brushed it off, not really thinking about it. But afterwards, I realized that by doing this, I did have legitimate data of exactly where a boat was crossing the Southern Hemisphere, and that maybe with that data, I'd be able to do some virtual observations of how fast it was going and where it was traveling. So I was able to plot out these specific pings on Google Earth. Now, you'll notice there's a gap in a couple of spots in the beginning. I honestly don't know if those emails didn't come through or if I accidentally deleted them because I did not have the forethought to retain them. But since then, trust me, I have retained every email I've gotten from this website. And on Google Earth, you can see that the general line from these two harbors is straight. It is a straight trek across the globe, the Great Circle Route. And on that Great Circle Route, according to every measurement ever made by any sailor, ever, and by Google Earth, and by every map utilized by governments and private citizens who sail boats across the ocean, the distance between these two harbors is just over 10,000 kilometers. And this trek was made over about 12 days. And utilizing the simple Jaren math, distance divided by time, the Olivia Maersk was traveling at approximately 35 kilometers per hour, or 18.8 knots. But that's not why we're here today. We want to see what the Olivia Maersk did on the Flat Earth map. Now, I could do the math like I did last week, airport to airport, or harbor to harbor. But in this case, I don't need to do the port to port. because I actually know the exact locations during the trek. Last week, I didn't know the exact locations of the airplanes because they drop off of tracking after they get over the open ocean. But this week, I have the exact locations as the Olivia Marisk traveled across the Southern Hemisphere. And you can clearly see that it is not a straight line according to the AE map. Now all we need to do is some basic math. First thing we need to know is the distance between the North Pole and each of these ping locations. Now, utilizing the longitude locations for each of these points, we're able to identify what the inner angle is between these locations. So now we have the lengths of two sides of our triangle, we have the inner angle of our triangle, and with that and basic geometry, we can identify the distance between these ping marks. Now remember, on the globe, the distance port to port was 10,000 kilometers at 18.8 knots of speed. But on the AE map, we don't double our distance. We more than double it to just under 25,000 kilometers traveled by the Olivia Marisk in 12 days. And with that distance divided by time, we're not doing 18 knots. We're doing 43 knots, more than double the speed of the boat. So now I ask you to remember, back to the beginning of this presentation, that the sun does travel 15 degrees across the plane every hour, and that based on that location on the line of longitude is measurable simply based on the location of the sun at that time of day to determine the distance between the two locations. And using this simple formula and this basic information, if the AE map were true, the Southern Hemisphere is vastly larger than anybody has ever accounted for. And if it's that much larger, then not only are airplane flights impossible, Jaron has tracked them across the ocean, and I've checked his math, and I've tracked boats across the ocean, and unless I've missed something drastic, I don't think my numbers are wrong, but I invite you to check my math. Thank you for your time.